Okay, hello everyone. So in this video we're going to discuss the concept of a homogeneous differential equation and how to solve it. But in order to do that we need first the concept of a homogeneous function. So a function of two variables, f of x, y, is called homogeneous of degree alpha if it satisfies this equation here for all x, for all y, and all t. The only thing that's constant is the alpha here. Okay, so just to give you an example, for instance, if we take f of x, y to just equal multiplication, then if I take f of tx, ty, this is going to end up just being t squared times xy, because it'll be tx times ty, which is just t squared xy. And that's just equal to t squared f of xy. So you can see here that this function f here is then going to be homogeneous of degree 2 because the alpha is, in this case, just 2. So this here is a degree 2 homogeneous function. Another example of a degree 2 homogeneous function could be just for instance, if we took g of xy, just equal to, let's say, y squared, because then if I had to take f of tx, ty, this would just be t of t times y squared, which is t squared y squared. And I said f instead of g, apologies for that. And this is just equal to t squared times g of xy. So that's also homogeneous of degree 2. Okay, and then a nice property of homogeneous functions is if you are given two homogeneous functions, so I'll just write this down as a property here. If f of xy and g of xy are homogeneous of degree alpha, then so is their sum. Okay. So that's the concept of a homogeneous function and just a basic property about them. So now we're ready to discuss the concept of a homogeneous differential equation, and here's that definition. So a homogeneous differential equation is any differential equation of the form here, given in this yellow box. So it consists of a two-variable function m times dx plus a two-variable function n times dy. And then we say that this differential equation here is homogeneous if these two functions are both homogeneous functions of the same degree. So both m and n here are homogeneous of the same degree. And it's very important that they're of the same degree. So a very simple example is given here. So if m xy is just equal to x plus y, and over here it's just equal to x, then both of these are homogeneous of degree degree 1. And similarly, if we look at this equation at the bottom here, then this will turn out to be homogeneous of degree 2. And likewise, this x squared we saw earlier is homogeneous of degree 2. So why, you may be saying, how could you quickly see that this expression here is homogeneous of degree 2? Well, one way to quickly see that is that it's a sum of homogeneous functions of degree 2. We saw on the previous page, we just go up again, that g of xy equal to y squared and f of xy equal to xy both have degree 2. So that means that their sum, according to this property here, also has degree 2. Great, so this is just a sum. This has degree 2, that has degree 2, and that has degree 2. And so the entire function has degree 2. homogeneous of degree 2. And likewise, we've already seen that g of xy equal to y squared is of degree 2, and so also x squared. All right, so that is what is a homogeneous differential equation. And now the next question is, how do we solve homogeneous differential equations? And to solve them, it's quite simple. We just make a substitution. Make a substitution y equal to xu or x equal to yu. And of course you can choose. You can choose, it doesn't really matter which one you choose. You're free to choose whichever you prefer. In fact, after a bit of practice, one can see which is going to help a lot. Essentially, of the m and of the n, whichever is the less complicated, one should make the substitution according to the variable, the d, whatever is in front. If what's in front of the dy is simpler, then this tends to be a good substitution. Okay, so let's see this in action. Let's consider this differential equation as we saw it earlier. So according to our technique, we should let u. Well, this is first, just to say it again, it's homogeneous of degree 1, but maybe we should just mention what the substitution is here, because what's in front of the dy is simple. It's just a negative x. Let's just say that this is equal to xu. And then we want to make a substitution involving, removing everything involving y and replacing it with something involving x and u. So in particular, dy here becomes just u times dx plus x times du. And then this equation here just becomes x plus xu, because that's what y is. So that times dx. And now I'm just going to shift the negative x dy over to the right-hand side of the equation. And then we just have x times dy, and we've computed what is dy. That's just going to be u times dx plus x times du. And again, that just came in because of the dy here. Okay, now this equation is always going to be a separable equation. So to solve it, what we can do now is just we need to get everything involving x to one side and everything involving u to the other. So just a quick argument here. If I multiply the x in here, then I'm going to have a term x u dx. And that, when I shift it over here, will actually cancel out with this x u dx over here. So just simplifying, we're going to get x dx is equal to x squared du. And this becomes a simple equation, just dx is equal to x du. Okay, so x dx is equal to du. So now you can just integrate, well, you can just first separate the variables properly. So we get 1 over x dx is equal to du. And now you can integrate both sides. So the integral of 1 over x dx should be equal to the integral of du. Okay, great. So here we have natural log absolute value x is just equal to u plus c. And so we get that natural log x is equal to, now we want to, at the end of solving a differential equation, get some relationship between x and y, and the best case is y is equal to something involving x, which is equal to a function of x. So we need to, at some point, replace the u by whatever it is in terms of x and y. And in this case, it's going to be y divided by x. So here, we're going to just get y divided by x here plus c. And we can simplify this further. we can say that y divided by x is just equal to natural log x plus c. Just to say how this happened, I just shifted the c over, and then because it's an arbitrary constant, we don't have to change the sign. It should become negative, but then because it's arbitrary constant, it can remain positive. Okay, good. And so this gives us our expression for y. Y is just equal to x natural log x plus c times x. Okay, so that solves our first example. And one should always just check at the end, once you've got an expression for the solution, you could always just differentiate, find dy dx, and then substitute it back into this equation and check your solution. Okay, let's do one last example, and then that can be this video. So here we're given a homogeneous differential equation of degree 2. And so because each term, as we saw earlier, is of degree 2. So we make a substitution, and the u here is going to be just as, we make a substitution y is equal to ux, just as we did in the previous example. So we're going to get dy is equal to x du plus u dx. And then we have to substitute that back into this equation here. So we're going to get x squared plus x squared u plus x squared u squared, because now I'm just, the xy became this term, and then the y squared became this term. So that deals with everything involving in front of the dx. And that should be equal to, and I'm shifting this term here over to the right of the equality. So that should be equal to x squared times dy, which is x du plus u dx. Good. So this is then dy. All right, so now we've made the substitution. The next step is always to simplify. And just to note something here again, if I multiply the x squared in here, I'm going to get a term x squared u dx. But then if I had to multiply this dx in here, I would also get an x squared u dx. So actually they'll cancel out, and I'll be left with just x squared plus x squared u dx is equal to just x squared times x, which is x cubed du. Okay, nice. And this is just going to give us 1 plus u dx is equal to x times du. Sorry, I should say u squared. There's a u squared here, because we cancelled this term and not the x squared u squared. Okay, so this is u squared here. And now this is separable differential equation, so let's solve it. We get 1 over dx, 1 over x dx is equal to 1 over 1 plus u squared du. And now we integrate both sides. And we get 1 over 1 plus u squared du. And this is just going to give us natural log absolute value x is equal to, now the derivative of, what derivative gives us this? It's just one to know, it's arctan. So arctan and then plus c. Okay, so that means that our final solution, so just as in the previous example, we had to replace the u by something involving x and y. Here we do the same, so the u again here becomes y divided by x, and so we have this, and this is implicitly defining the function y. Okay, so that does it for this video. By the way, just to mention, using this condition here, if you were to restrict y to specific other conditions, initial values, and so on, what interval is defined on, you could get an explicit formula for what is y. But this is also good enough. Okay, thank you.